Okay, so welcome to the 16th video in the discrete structures series, and this video is going to resume our discussions from our last video. So we're going to look at division of binary integers, and then we'll have a detailed look in the idea of modular exponentiation. And before diving into the division of binary integers, I want to recall that in our last video, we looked into the algorithms for multiplication and addition. But the division algorithm that we use here is going to use repeated subtraction. So in that regard, the subtraction algorithm is something that we have not looked at, but given the operations multiplication and addition, the subtraction follows. For example, given any number, I can multiply it with a -1 and then add it with any other number to get the effect of subtraction. Okay, so let's look into our first topic of division of binary integers. So the division of binary integers. Alright, so let's look into a numerical example that demonstrates this process of division, and then we'll try to convert that into a pseudocode or an algorithm. And so let's consider this division, 26 divided by 8. Okay, so 26 is my number A, and I'm dividing it by a divisor D. And ahead of time, I could tell that the quotient of this operation would be 3, and then the remainder would be 2. Because as always, 8 times 3 is 24, and then adding 2 would result to 26. So how do I demonstrate the same process using repeated subtraction? I'm going to start this way. I'm going to assume that my remainder is initially the original number, 26. And I want to start with a quotient of 0. And from here, I'm going to repeatedly subtract the value of the divisor D until my remainder falls within the range of the divisor. Because ultimately, my goal is to have this remainder be between 0 and 7. And after one pass of subtraction, after subtracting 8 from 26 once, my remainder remaining would be 18, and then my quotient would be 1. It would increase by 1 from 0 to 1. Okay, and 18 is still bigger than my divisor D, so I want to repeat the process again. So after subtracting 8 one more time, I will have R equals 10 and then a quotient of 2. 10 is still greater than 8. Do it one more time. I have R is equals to 2 and then quotient equals to 3. And since this 2 is now less than 8, I stop. And that leads me to my quotient of 3 and the remainder of 2. And what would happen if this number was an exact multiple of 8? Well, at some point I would end up with a remainder of 8, right? And I would do one more division to give me a remainder of 0 and quotient would rise one more time. So no matter what happens, my remainder is going to be between 0 and 7. I have to ensure that. So it has to be positive and between 0 and 7. And before I start my algorithm, I want to look at one more case. What happens if this number is negative? See, I still want to get a positive remainder. So let's say I'm dividing a -26 by 8. How can I ensure a positive remainder? To make it easy, let's break it down. Originally, I had 26, and how did I end up with a quotient of 3 and remainder of 2? I expressed 26 as 3 times 8 plus 2, okay? So my divisor 8 is here, 3 is my quotient, and R is my remainder. I want to do a similar thing with -26, but still get a positive remainder. So let me start by writing the analogous negative expression for this, and that would be -26 equals, and this time I would use -3 for my quotient, okay? And this would be times 8, and then plus remainder would be -2. And this equation is still valid because -26 is -24 and -2. But I don't want a negative remainder, and I ensure that by taking the product one more time. Okay, so I want to express this as -4 times 8 plus 6. Okay, and that will give me a positive remainder of 6. And I want you to see that this should not be much confusing. I have expressed 26 as 8 times 3, and that is 24. And this is the closest multiple of 8 that is smaller than 26. Okay, but when I'm looking at the negative numbers, the smaller numbers have even bigger magnitudes. For example, -28 is smaller than -26. So I'm doing the same thing here. I'm looking at a multiple of 8 that is just smaller than -26, and that in my case would be -32. And doing that leaves me a positive remainder of 6. So the pattern that we want to observe here is what happened to the quotient and the remainder. So when I did 26 divided by 8, I got a quotient of 3 and a remainder of 2. But when I flipped the sign of 26, see what happened to the quotient. Quotient went from 3 to 4, but it changed its sign. So then the new quotient in this case would be negative times the previous quotient plus 1. Okay, and this is something that we'll use in our algorithm later. And also in the case when this is negative, I have to make one more change also to the remainder. The remainder changed from 2 to 6, right? And that is my divisor minus the remainder. So if taking a positive quotient here gave me a remainder of 2, taking a negative quotient would give me a remainder of 8 minus 2. Okay, and I have to adjust the remainder in that case to my divisor minus R. And of course, this is only when the number is negative. So when I'm designing my algorithm, I'll start by pretending that the numbers are always positive and then make this modification at the end if they were negative. Okay, that's gonna be my approach to the algorithm. Okay, so now we are ready to show our algorithm, but I want you guys to focus on this segment that I placed here. This is the result from earlier. And we need to do this if the number that we need to divide is negative, right? So negative a. Okay, so I want to put the algorithm here. So the procedure for division, and it takes any a that I want to divide by a given d. And we already know the assumptions of division. This a is going to be any integer, while d is only going to be a natural number. So we discussed why that is in one of our earlier videos. So those assumptions are here. Okay, so now we start implementing the algorithm. So first we start by setting the quotient to 0. That is the first step as we saw earlier. And then I want to set my remainder to the modulus of a. Okay, so even if the number is initially negative, I'll just use the positive sign of it in order to perform the division, and then I'll use these results in order to modify it. And now I'm ready to perform the repeated subtraction, and that needs to happen while r is greater than or equal to my divisor d. And as soon as this doesn't happen, the loop doesn't execute. Okay, so whatever block of code I write here is only true while this is happening. So perform a subtraction on the remainder. R is equals to r minus d. That's my first step. And then increase the quotient by a 1. Q is equals to q plus 1. And if I do this while r is greater than or equal to d, eventually r is going to be smaller than d, and this loop is going to terminate. Okay. And when this loop terminates, I'm ready to output q and r, but I need to be careful to also make this adjustment if a was originally negative. So let's do that. So I want to say if a is less than 0 and r is greater than 0, because this is the case that would happen if a were initially negative. Then you remember we want to modify our quotient this way and remainder this way. So the remainder would be updated as follows: d minus r. So we subtract the remainder from the divisor in this case. And you see the quotient transforms in this way. So quotient becomes the negative sign of q plus 1. Okay, and we do this only if this case is true. That is if originally my number was negative. And finally, I can return q and r from my algorithm. Okay, so next we have a look at the modular exponentiation algorithm. Let's have a look at this problem. I want to calculate what the value of 4 power 287 mod 3 is. Okay. And conceptually, it's pretty simple, right? I need to evaluate this number and see what the remainder is when divided by 3. But the problem lies in calculating 4 raised to the power of 287. This is a significantly huge number. So the goal here is to find a way to calculate this without calculating 4 to the power 287. And then for our purpose, we'll find a way to optimize it if the number in the exponent is binary. Okay, so let me start by making a few notes here. So the first one is take the modulus before the exponent. So for example, if I have 4 to the power 287 mod 3, taking mod 3 of the base value doesn't change the result. Okay, so this is the same as 4 mod 3 raised to the power 287 mod 3. And this is one rule that we'll be careful about, and this will just be equal to 1 to the power 287 mod 3 and would be equal to 1. So this rule is pretty neat because it allows me to simplify this into this expression. But still the result of this modulus is not guaranteed to be a 1. I chose this example intentionally so that I would get a power of 1, but that may not always be true. But what is guaranteed is that this process will bring in my base. Whatever the base is, it will bring the base within the modulus. Okay, so for 3, I could get 1 to the power something or 2 to the power something. And this process already simplifies the result by a lot, but we'll look at one more property of modulus that will help us simplify it even more. So second, I want to call take mod before multiplying. Okay. So let's say I want to evaluate 3 to the power 3 mod 5. So what would I do normally? I would start by calculating 3 to the power 3 and then I would take the modulus of 5. And let me show you how we can improve on that. See, so how do I actually calculate 3 to the power 3? So I start with a 3 and then I multiply with a 3 and then a 3 again, right? But since I need to take all of this mod 5, every time I multiply, I can immediately take mod 5 before doing the next multiplication, and that would end up in the same result. So for example, 3 to the power 3 mod 5 is 2 because 27 mod 5 leaves a remainder of 2. And let us see what happens here. I do one multiplication 3 times 3 and that gives me 9. And before multiplying 9 with these 3, I immediately take mod 5. Okay, so 9 mod 5 is 4. And then instead of doing 9 times 3, I can just do 4 times 3 and that gives me 12. And then I can take mod 5 again and that would give me 2, which is the same result. Okay, so this is going to be extremely important in the algorithm that we are going to design here. And one more point, to make the algorithm optimal, I'll not start with a 3 and multiply 2 times, but I'll start with a 1 and multiply 3 times. Because 1 is the multiplicative identity and doing that has some advantages in the algorithm. But the point here is after every multiplication, before you do the next multiplication, you want to take the modulus first. And that will prevent your numbers from growing too big. Okay, now we are ready for the third and the main point, and we'll be implementing our algorithm after this one. So what if my exponent is a binary number? So let's say I need to calculate any number b raised to the power 5. But this 5 is given to me in binary representation 1, 0, 1 on base 2. Okay, and you already know that the binary numbers correspond to the power of 2. So this one corresponds to 2 to the power 0, 2 to the power 1 here, and 2 to the power 2 over here. And that makes sense, right? This is 4 that gets included. This one doesn't. This is 1 that gets included. So 4 and 1 add up to 5. So what I can do here is to break b as the power of exponents. See, it is always true to say that b to the power 5 is equal to b cubed times b squared. And I want to do something similar to this, but I don't want to choose these numbers randomly, 3 and 2. So if I can break this number into sums of powers of 2, that would make it easier to work with binary numbers. So instead of 3 and 2, I want to write b to the power 5 equals b to the power 4 times b. Okay, and that is b to the power 1. And this is always possible to do for any number, because every number will have its binary equivalent, right? And the binary equivalent will give me which powers of 2 I should include. So more precisely, I should be saying b to the power 4 into 1, because this one is being included, times b to the power 2 into 0, because this one is being excluded. And for this term, it's going to be b times 1 into 1, because 2 to the power 0 is 1, and this one comes from the fact that I'm trying to include it. So we can observe from here that if my exponent is a binary number, I can break it as a product of powers of 2, and I should choose to only multiply those b's which have a non-zero power, right? Because the 0 power will just be 1. And therefore b to the power 5 is just b to the power 4 times b to the power 1. But how does this help us in the algorithm? Because now I can calculate the exponent by simply doing a pass on these numbers. You can see I just needed to calculate b here, b square here, b to the power 4 here. Okay, and 4 plus 2 plus 1 is 5. And you'll also notice that this value is just the square of this, and this value is also just the square of this. So each time I grow into a new term, all I need to do is to square the previous term. And as I keep calculating and multiplying these values, I will make sure to only include the powers of 2 that have a corresponding 1 in my binary number. If the corresponding number is 0, that won't be included. If the corresponding number is 1, those will be included. And you know this rule, right? Take mod before multiplying. So in order to calculate the whole thing mod m, so let's say I need to calculate b to the power 5 mod m. So we deduce this would be equal to b to the power 4 times b to the power 1 mod m, right? This only has 2 terms, but imagine this having more terms. And each time I would just multiply 2 terms, take the mod m, and then take another term, mod m, and so on. Okay, and in this example, I want to clarify one more point. The representation of 5 was 101, and that told me that I had to calculate b and b to the power 4. But I'll have to calculate b to the power 4 from b squared, okay? I take b and then square, b square, and then square again, I get b to the power 4. So regardless of the value being 0 or 1, this I have to calculate. So in my algorithm, I will calculate all the squares, but I'll only multiply and mod m for the bits that are 1. The algorithm itself is not too long, but all of these things are going inside of it, and if you want to make absolute sense of it, it may be worth looking into these things again. Okay, now I'll dive into the algorithm. So this is going to be my procedure. So let me call this mod x for modular exponentiation. And I need 3 inputs, right? b to the power n mod m. So I'm going to take those. I want to start by considering my base b and the exponent of 5 here. Let's call that n. And I want n to use a binary notation. Okay. And I also have my modulo factor of m as an input to this procedure. Okay. So I'll begin my procedure by initializing my result as a 1. Because as we talked about earlier, 1 is the multiplicative identity. I want to start multiplying things to 1 and accumulate the result in this variable. And you should remember from earlier, the first thing that we want to do is to normalize the base within the modulus. So if I'm looking at something like 4 to the power n mod 3, I want to take 4 mod 3 first, right? And then only take the power of n and mod 3. So if you are unclear about this, please go back and see why. So I'm going to say my product is equals to b mod m. Because whatever base I'm using, I want to bring that base within the modulus first. And we saw earlier that doing that doesn't change the result of the modulus. And the reason we have 2 variables here, result and product, is also something that we discussed earlier. As I pass through the digits of n, I only want to multiply and accumulate the result for the bits that are 1. But I'll still need to keep track of the full product for all the bits to come, regardless of them being 0 or 1. And that is analogous to saying, I'm not including this 0 here. The contribution from this power is not going into my result, but I still need to calculate this in order to calculate the next one. So the product will be a variable that will keep track of all the powers, while the result will only borrow from the product for the terms that are 1. So now let me begin my loop of the digits of n. So for any variable, let's say I is equals to 0 to k minus 1. I don't want to use the same variable n here. So let's make this k. So I'm looping from 0 to k minus 1, from the first bit to the last bit. Okay, so now let's begin the block of my loop. So for each iteration of this loop, I want to accumulate the result only for the digits that are 1. But I want to keep calculating the product regardless of the value of the digit being 0 or 1. So if ai equals to 1, that means the bit that I'm currently scanning is a 1. And in this case, I would say result equals result into product mod m, right? Because take mod before multiplying again. Before this loop goes into the next iteration and multiplies again, I'm just reducing the result modulo m. And you see, this I want to do only if the current digit is a 1. But I still need to update my product regardless of the bit being 0 or 1. So let me do that. And I could say unconditionally, my product is always going to update. Product is going to be product times product mod m. Okay. And then I could end my loop here. So for each digit in my binary number, so this step is like calculating the powers of 2, right? So calculate 2 power 0 and 2 power 1 and 2 power 2 anyway, but only multiply that to the result and take the modulus if the corresponding bit is a 1. So when I perform this routine, the algebra that we discussed here will be carried out and the result of the modular exponentiation b power n mod m will be available in the result variable. So I think this was a little sketchy and I think this is a little bit challenging to understand. So if you have any questions regarding this, please feel free to ask in the comments. And if you don't understand the algorithm for some reason, make sure to go back and watch these requisites again, the 3 points that we discussed. And once you understand them clearly, this algorithm should also follow. Alright, so that was all the discussion for this video. We'll start next video with the applications of number theory. One of the applications we already discussed, the extended Euclidean algorithm in our previous video. So we'll be looking at the remaining ones. So that's cryptology and the Chinese remainder theorem. So that is it for this video. I'll see you guys in the next one. Have a good day and bye.